ever just felt completely swamped, by the sheer amount of information hitting you every day? Articles, news, research, posts. It feels less like a stream and more like a tsunami, right? That's really why we started the deep dive. Our mission is pretty simple. Cut through all that noise. We grab a stack of sources, the ones you actually send us, and we pull out the most important nuggets of knowledge. We want to help you get well informed, fast, and hopefully have a few of those aha moments.
And today, yeah, we're taking a really close look at something that's, well, changing things fast. Large language models, LLMs, these are the AI tools, really powerful ones that are fundamentally shifting how we interact with tech, with information itself.
It's kind of incredible, isn't it? So for this deep dive, we've gathered your sources on LLMs, everything from, the basics of how they work to really practical tips for using them day to day. Our goal here is to find those surprising facts, those crucial insights that'll give you a real sort of intuitive grasp of how these systems operate. Get ready to maybe see them in a bit of a new light.
Okay, so let's start there. When we say large language model, what does large actually mean for us, the users? Is it just size or?
That's a great starting point because large is definitely key. It points to two main things. First, just the vast amount of training data these models learn from. We're talking trillions of words scraped from the internet, like 45 terabytes of text data, books, articles, websites. Just to give you a sense of scale, 45 terabytes. That's like a stack of books reaching the moon multiple times.
Wow. Okay, that's large. And the second thing, you mentioned parameters, right? The second part of large is the incredible number of parameters they have. Take GPT-3, for example, a pretty well-known one. It has 175 billion parameters. Think of parameters like tiny adjustable knobs inside the LLMs, a digital brain. 175 billion of them. That's, well, way more knobs than stars in our galaxy, apparently. Each one is fine-tuned to help it spot patterns and predict language. They're essentially the learned connections, the knowledge inside the model.
Okay, 175 billion knobs. Got it. And then the language part, that seems straightforward, but maybe it's not. It means they're trained on and understand natural language, right? The way we actually speak and write, not code.
Exactly.
Yeah.
That's what makes them feel so accessible, natural language. And finally, model just means it's an AI system trained for specific tasks. Oh, and it's important to draw a line between the model, the core AI brain, let's say, and the chatbot.
Yeah.
The chatbot is just the application, the front end, like ChatGPT or GitHub Copilot, that lets you talk to the model.
Right, the interface versus the engine. And one of the sources you sent in really stressed this point. LLMs aren't just about text anymore. Older models like GPT-3, yeah, they were text-based. But the newer ones, like GPT-4, they can handle multiple types of input and output.
Yes, exactly. That's what we call multimodality. GPT-4, for instance, can process text and images in the same conversation. Some of the really cutting-edge models are even starting to work with audio. This multimodal thing also affects how they handle up-to-date information. There's this concept called the knowledge cutoff date.
Ah, I've heard of that. It's basically the use-by date for the training data, right? The point when the AI's knowledge stops.
Pretty much, yeah. The moment in time when the data feeding the AI was last updated.
So if something happened after that date, the basic model just wouldn't know about it. Does that mean they're always out of date? Or is there a workaround?
That's a really crucial question. And it's where multimodality gets, well, clever, but also a bit tricky. Because they can often browse the internet, newer LLMs can actually try to answer questions about things that happened after their cutoff date. They search for current info.
Okay, but I've heard stories, maybe you have too, about them just making things up sometimes. Hallucinations, they call them. Is that a risk when they search online?
Unfortunately, yes, it can be. When they're reaching beyond their core training data, the accuracy isn't guaranteed. You might get responses that seem plausible but are actually fabricated. Hallucinations is the term, yeah. It's important to remember they're designed to predict coherent text. And sometimes that predicted text just isn't factual.
That really underlines the idea that they aren't thinking like humans do. Okay, so if they're not thinking, how do they actually process all this language? What are they working with?
Great question. This brings us to tokens. Think of tokens as the fundamental building blocks of language for an LLM, like Lego bricks for building a sentence. A token could be a whole word, sometimes just a punctuation mark, or even just part of a word, like the word unbelievable might get broken down into unbelieve and able. 3 separate tokens.
Huh. And get this, according to OpenAI, roughly 1 token equals about 3/4 of a word, 0.75 words. So when you see costs or limits mentioned in tokens, you can kind of estimate the word count.
Exactly. And this leads to the tokenization process. When you feed text into an LLM, step 1 is it takes your input. Step 2, it breaks it down, splits it into those words and parts of words. Step 3, each little piece gets mapped to a unique number, a token ID, using a big dictionary the model learned during training.
So if you type hello world, the model doesn't see those words. It sees numbers like 154969950 or something similar. And for you, the listener, understanding tokens is actually pretty important. It affects how much the LLM can remember in a conversation, how fast it works, and even how much it costs if you're using an API. Every word in, every word out, it's a token you're using or paying for.
That's a really key insight. And it ties into another common misunderstanding. LLMs do not have true understanding, no consciousness. They aren't thinking in the way we mean it.
So no HAL 9000 in there just yet. It's actually something simpler, but maybe even more amazing in a way. They're just predicting the next word.
Exactly. It's a highly sophisticated version of what people sometimes call a word-guessing machine.
Hmm.
But the sophistication is immense. They learn all these patterns, structures, relationships from that massive training data. When you give them a prompt, they analyze the context, your input, and then they calculate probabilities for tons of possible next words and pick the one that seems most likely.
What's also kind of wild is that they're non-deterministic. I've definitely seen this. You give an LLM the exact same prompt twice, you might get two different answers.
That's right. It adds this element of, well, unpredictability.
Hmm.
Experimentation, maybe. It means there isn't always just one single correct output from the model for a given input. It can surprise you.
Okay, this gets really fascinating when you think about the sheer computing power involved. Let's try to peek inside the LLM's brain for a second, connecting back to those parameters we mentioned. GPT-3, 175 billion parameters, 96 layers, trained on 300 billion tokens. Massive numbers.
Now, think about the computational work. To predict just one single next word. Let's say after you type Mary had a, the model has to process all 175 billion parameters through all 96 layers.
Wait, hang on. For every single word it generates, it has to run that entire calculation again, through all those billions of parameters and dozens of layers.
That's exactly right. It's not one big calculation for the whole sentence or paragraph. It's an iterative prediction process, repeated for each and every word, or rather, token, it outputs.
Wow. That's astonishing. The sheer scale of computation happening just for it to type the next word.
It really gives you a sense of what's going on under the hood.
Okay, so what does all this mean for you listening right now? How can you actually use these tools effectively? First off, choosing which LLM to use. You've got options, but for really good results, probably best to start with the leading ones, right?
Yeah, definitely. When you're picking a model, a couple stand out. There's ChatGPT, especially the GPT 4.0 version.
Yeah.
It's free to use, which is great, though the free version has a daily message cap and no image generation.
Mhm.
You could upgrade to ChatGPT Plus, usually around $20 a month, for more features, higher limits.
And the other big one, especially if you're into open source, that would be Llama 3. It's top tier. It's free if your own computer can handle it, and it takes both text and images as input. But the key thing is the techniques we're talking about, they generally apply across different LLMs, so you can experiment.
Definitely. Now, for maybe the biggest aha moment in actually using them effectively, prompt engineering. I remember my first attempts trying to get an LLM to code a game. It was frustrating. The code was often buggy or incomplete.
Oh, I've been there. Let's walk through a practical example. Let's say you want to create a snake game in Python using ChatGPT. First try, you might just ask, create a snake game in Python. Simple enough, right?
Seems simple, but what often happens is you get code that runs, maybe, but it might be missing something crucial, like the actual snake. It highlights that the AI doesn't understand snake game. It's just predicting text patterns it's associated with Python and game, trying to complete the sequence you started.
So less intelligence, more like super advanced predictive text based on trillions of examples. That's a key takeaway. Okay, so for the second try, the successful one, we changed the approach. First, in the same chat, we asked something like, what are all the features I need to include in a good snake game? Then, after it listed them, we followed up with, okay, now provide Python code for a snake game that includes all those features you just mentioned.
And that iterative, more specific approach, it usually results in much better, fully functional code. The lesson here is huge. Clear instructions, breaking down complex tasks into smaller, specific steps in the same conversation. It dramatically improves the output. It's often less about what you ask and more about how you ask it. That's prompt engineering in a nutshell.
That's a really practical tip. Now, for those of you wanting to get hands-on, maybe beyond the free chatbots, let's quickly touch on setup and managing usage. We can use OpenAI's Playground as an example. First step is generating API keys, and we really have to stress this. Keep these keys private, never share them. Usage is tied directly to your account and, well, your wallet.
Absolutely.
Yeah.
And inside the playground, you can monitor your usage. You're charged per token, remember, roughly a word. Just be mindful. Long conversations, big documents, they can chew through tokens pretty quickly, so keep an eye on the meter.
And finally, managing the money side. In settings and billing, you'll link a credit card and add funds. Our advice, start small, maybe just $5 to get a feel for the costs. And critically, under settings and limits, set a maximum monthly spend. This prevents any nasty surprises on your bill. You can also set email alerts for spending thresholds. It's just smart practice for experimenting safely.
Right. So as we start to wrap up this deep dive, we've really covered quite a bit today, haven't we? From defining LLMs, understanding their multimodal skills, that whole world of tokens, to getting a handle on how they think, or rather how they predict probabilities, and the practical side of prompting and managing usage. You should now have a pretty solid foundation for understanding these tools.
It's definitely been an exploration. So as we leave you today, here's a final thought to chew on. Given that these LLMs fundamentally work by predicting the most probable next word based on patterns they've learned, without any real understanding or consciousness behind it, how might that core mechanism shape the future of AI? And what does it mean for us as users as we interact more and more and maybe even come to rely on these incredibly powerful yet fundamentally predictive systems? Something to think about.